The Internet of Things is changing. In the same way that constituent parts come together to form a stable ecosystem, so the Internet of Things is undergoing an evolution. The Internet of Things is evolving. In natural systems, isolated locations may evolve into a unique ecology, as long as outside competition remains restricted. But once such systems become exposed to competitors, they may need to adapt accordingly. Similarly, in the field of technology, self-contained systems can be found. Various factors allow dominant organizations to prevail in relative isolation. These include the following. First of all, market dominance. Early market development, acquisition, or a superior product are factors which may lead to an enterprise gaining a dominant advantage. The advantage of a captive market, or a desire to preserve brand quality, may encourage an organization to seek to perpetuate its position. A second factor, which may allow a company to prevail in relative isolation, is proprietary technology. If a company has in place protection, such as patented techniques, it can prevent competitors from encroaching on its territory. A third factor allowing companies to operate independently is the lack of standards and cooperation. A dominant company will not necessarily actively pursue standards compliance. It may simply not want to relinquish its market prominence, or it may not wish to sacrifice its hard-won development gains, or it may judge its own model to be superior. Fourthly, we can look at connectivity considerations. The ability of a dominant organization to play a role in the Internet of Things may depend on external global factors as much as its internal considerations. The capabilities of the communication medium in which Internet of Things organizations exist may determine the feasibility of Internet of Things connectivity. Cloud computing, optical fiber, new Internet of Things protocols, wireless improvements, and more IP addresses are amongst the developments which make Internet of Things more viable. So what about developments in the field of IoT device technology? What is true for the medium of communication is also true for the capabilities of devices. The emergence of cheaper constrained devices able to communicate wirelessly and securely is also driving the growth of IoT potential. So-called constrained devices are ones which are able to operate in an environment where limited resources are available in terms of processing power and bandwidth. The overall cost of development must also be considered. Ultimately, the question will arise whether the organization can sustain the cost of development, which may be ongoing and which requires the business to be nimble and responsive in the face of change. The word silo has been adopted to describe go-it-alone organizations which maintain a proprietary ecosystem of devices impermeable to third-party products. Originally denoting a separated place of storage, the term has been adopted in the information technology field to refer to a state of intentional isolation. As the Internet of Things develops, the silos become subject to new pressures. Silos may develop to take advantage of technical advances, such as cloud storage and a client base with more ample bandwidth, but can do so without necessarily committing to more thorough integration into IoT. So what do we mean when we use the phrase integration into IoT? Major companies have undertaken Internet of Things research since the term was conceived. Many are involved in various schemes to evolve a common language between devices and common terminology and syntax to structure communications. The question remains: what are the different forms of engagement which an organization can adopt with respect to IoT and the new schema? What many might think of as a typical smart technology application would be a smart building, a smart home, for example. Let's suppose that this smart building is populated with sensors. The building is also equipped with actuator devices to convert sensor signals into action. If all these devices are made by a single manufacturer and, furthermore, are able to communicate only with their own kind, then we might say that this scenario is typical of a silo-type business. Even though the building may have a broadband connection, this alone does not demonstrate significant integration with the Internet of Things. Let's now suppose that the devices in the building are made by different manufacturers. If they can still communicate freely between one another via a common protocol or language, in particular as defined by agreed standards, then this is a step towards Internet of Things integration. Let us suppose, furthermore, that some devices are constrained. Constrained devices have low processing power or poor connectivity media. Support for constrained devices is another quality which allows for fuller Internet of Things integration. So far, the part played by the Internet in this scenario has been limited to standard uses, such as remote backups, web browsing, and so on. Full integration into IoT implies that the Internet plays a more significant role. In a fully integrated IoT application, the Internet is pivotal. So let's now suppose that the smart building described earlier is a marine research establishment. It uses sensors and actuators to simulate the ocean environment for fish held in tanks. This research requires that specific ocean conditions are recreated in the tanks in real time. It achieves this by communicating with research vessels in the ocean. These vessels monitor temperatures on the seabed, and the results are relayed back to the research station via satellite. Sensors on the seabed, interacting with heat sensors and actuators in the fish tanks, ensure that the temperature conditions in the tanks copy those prevailing in the sea. This scenario now displays many characteristics typical of IoT applications. But one important element is missing from a full integration into IoT potential. Let's suppose that the Marine Research Centre now requires that sea nitrate levels be matched in the tanks as well as temperature. Deployment of additional nitrate sensors would be costly, but the centre discovers that another institution is conducting similar research into the effect of nitrate levels on ocean flora. This organisation is in a position to provide its data to the research centre. The research centre gets the necessary data without having to deploy its own nitrate sensors. The same sort of data transaction could be made with other partners. A business conducting a geological survey of deep-sea sediments, for example, may also be able to contribute useful data. As may an international body surveying fish stocks using seabed-located cameras. One organisation provides a service to the other. This in itself is nothing new. It is not uncommon for organisations to reach bilateral agreements. But the development of IoT changes the dynamic in several important ways. Firstly, in terms of the greater potential for direct connectivity of devices. Secondly, in terms of the expansion of potential data providers. Thirdly, because the Internet of Things allows for the development of a services marketplace. IoT sets the scene for a great proliferation of diverse available services. A service can be anything from permission for direct access to a data source to data which has been abstracted and analysed from IoT or other sources. But how can a service provider be matched to a user requiring that service? The service market, as well as providing a mechanism for a monetized transaction, can also facilitate finding a service match between provider and consumer. The services market can fulfill various functions. It can provide a framework for facilitating payment for a service. It can also act as a protocol gateway to enable different devices to communicate. It can develop algorithms and statistical models or identify connections in order to provide a service. It can offer advice to organizations wishing to integrate into IoT. It can also develop mechanisms for finding a service to match a given need. And it can develop a capability for identifying trends and predicting needs. So how might service markets develop? A market catering for all potential devices and services needs to be well organized if it is to be used successfully. An organization could be assisted in searching markets for a service, for example, via the use of service-optimized browsers. Indeed, service crawler software could traverse iOS markets in much the same way as robot software pores over the World Wide Web. But how can the Internet of Services information be organized? A syntax could be devised to provide a vocabulary for services, in the same way that an Internet of Things schema is being developed to allow devices to communicate. Alternatively, given the exponential rise in storage and processing power, the path to a desired service could be identified by statistical and heuristic analysis. Taking this model further, the need for a given service could conceivably be identified even before the service consumer organization is aware that the need exists. This is possible if the profile of the organization can be pieced together by artificial intelligence such that its future needs can be foreseen based on analysis of its current behavior. Its needs might also be predicted by an analysis of the consumption of clusters of services in the same sector. There is even scope for supposing that services might become commoditized and traded and invested as independent entities. Full integration of an organization into the Internet of Things also implies a commitment to the Internet of Services. The terms Internet of Things and Internet of Services both refer to vast and varied concepts. The types of organizations which might engage with or integrate into the Internet of Services and the Internet of Things are also multifarious and global in their scope. The two terms refer to different things, but are related in that both involve enabling a system of universal access via the Internet. The Internet of Things is concerned with devices, facilitating communication even for constrained units. The Internet of Services, meanwhile, makes available services not necessarily derived directly from the Internet of Things. The Internet of Things is of practical relevance to creators or users of Internet-savvy devices, whereas the Internet of Services is concerned with delivering service to an intermediary or end consumer. Internet of Services may become the more dominant phrase in terms of frequency of popular use, but this does not mean that it supersedes Internet of Things. The two terms refer to different concepts. For an organization that manufactures devices, integration into IoT can be clearly identified in terms of its willingness to engage in the following. Firstly, by making its products able to communicate with others via open protocols. Secondly, by making its products receptive to the possibilities of the Internet of Services. For non-manufacturing organizations, integration into the Internet of Things may be more indirect. For example, via the consumption of services generated from IoT, or via the adoption of IoT-capable devices, or the adoption of IoT-friendly policies. Other organizations may consume services without recognizing a direct connection with IoT. The service itself may consist of highly processed information from widely distributed sources, from which the final service is abstracted. Some services leverage IoT potential in a direct and simple fashion. Take the example of a delivery service. A fleet of vans delivers fish-themed wallpaper to widely spread customers. The organisation keeps track of its vans using a GPS device, which can transmit position data as well as calculate routes. The customer can be kept informed of the likely delivery time because the van position can be determined by satellite. Global Positioning Services, or GPS, were amongst the first to raise popular awareness of the potential of IoT and IoS. Here, the mapping of the hardware sensor, the GPS device, to the service, delivery tracking, is straightforward. Let us now suppose that the GPS data, combined with an anonymized identifier, are also forwarded via the road traffic furniture, in this case the lampposts, to a roadside fibre optic network. This in turn relays the information back to the servers of the Government Highways Department in the cloud. The data centre in the cloud now generates another service based on GPS data from all vehicles. This service is able to detect unusually high congestion on the roads and relay traffic warnings to service users. The Fish Wallpaper Company subscribes to this service to fine-tune its delivery predictions. In this case, a service has been derived indirectly in a more circuitous way. Firstly, the data is aggregated. Secondly, it is intensively analysed to identify traffic flow. The service user can use the information to predict delivery and avoid congestion. Now let's take another look at the driver.
Hello.
The driver wears a smart watch and gives consent for its data to be relayed anonymously to a Highways Department research centre. This information is accompanied by an identifier, which enables its information to be matched to the GPS data. The watch records health data. The information is transmitted. Data is aggregated from all users, and then the data is correlated with traffic congestion data using the anonymized identifier to match the data. Finally, the result is made available. In this case, we have two distinct types of hardware sensor. The GPS route finder, or tracking device, and the smart health watch. Both GPS tracker and smart watch can provide independent services, or, as here, the aggregated data from both can be amalgamated, in this case by a government department to create a new service which publicises correlations between health parameters and traffic conditions. The Fish Wallpaper Company can use this information to consider the impact of rush hour traffic on the health of its drivers. If the government study furthermore incorporates information from a database of national events and weather data, it can offer a predictive service which can recommend how to avoid traffic congestion and undue stress to drivers. There are several points which arise from this. Firstly, it is easy to see how the results of two analyses may combine to form a new service. Secondly, the connection with Internet of Things devices becomes abstracted into the service. Thirdly, data can be drawn in from other sources, such as databases. And fourthly, that analysis can give rise to an indication of future trends. This is still a simple example, but it is clear to see how services and their sources can ramify and grow in complexity. It can also be seen that the drawing into a service of many tributary analyses can add value to the end service product. As well as data generated by IoT and input from databases and complex algorithms, the influence of social media on the development of services is highly significant. Information gathered from social sources, such as behavior data and personal preferences, is central to the functionality of many services. The Fish Wallpaper Company manufactures a smart wallpaper, the pixels or light points of which can be recolored remotely. A wallpaper user allows data to be collected from their social media channels and used to assess their mood or activity state. User social data is gathered, the content is analysed. Analysis assesses the mood of the user based on vocabulary and frequency analysis. The wallpaper tone then adjusts according to the user mood. In addition, each individual fish can be identified with a social media contact and made to light up when the associated user is online. This is all very well, but the Fish Wallpaper Company has a competitor, which makes a similar wallpaper featuring rabbits. In order to get ahead, the Fish Wallpaper Company develops its digital strategy. The wallpaper background will now respond to ambient conditions. The sun, dapple and shadows will move with a variable frequency. The movement frequency will correspond to changes in lighting. When the lux level is high, the shadows will move subtly more quickly. To achieve this, the business will need to harvest data from lighting sensors in the room. Instead of engineering this data transfer locally, where the wallpaper is installed, an IoT IoS integrated lux sensor manufacturer will be found, which can provide a subscription service in the cloud, after which the lux data can be relayed back to the property to effect changes in the wallpaper background accordingly. The fish wallpaper business implements the changes and gains a competitive advantage. These examples may seem eccentric or outlandish, but it is partly the nature of IoT and IoS to expect the unexpected. The beginnings of IoT mark an inflection point in development, from which an exponential growth of new technological relationships becomes possible. In this last example, the connection takes place in the cloud, even though the Lux sensor and the wallpaper are located in the same apartment. This is convenient because the Lux sensor can provide a standardized interface made available through the iOS marketplace. The Lux data is tagged with an identifier for that particular apartment, and measures are put in place to ensure that all data remains secure. It is because both businesses are integrated into the Internet of Things and Internet of Services that they are able to complete this transaction simply, using the Internet of Services marketplace, without the need for any physical intervention. Before the sensor business made its data available as an Internet of Services interface, it would have been necessary for an engineer to attend the apartment, to cable in a connection and make a custom configuration. This example illustrates a change of emphasis which may be required in business thinking. The solution relied on a degree of lateral thinking. It also shows the need for what might be termed horizontal thinking. A business which has been accustomed to developing a silo product in a vertical market may now find that its product can be enhanced by taking advantage of data services which might originate from a completely unrelated sector. The same applies to businesses with a broad customer base. New opportunities may derive from participants in seemingly unrelated markets. A change of perspective is required to actively seek out new connections. This alternative thinking is characterized by broader perspectives, lateral thinking and creative structures, adaptation to disruption and investment in change, greater forward planning and analysis, and cooperation and communication between sectors. Internet of Things and Internet of Services thinking can apply to the internal workings of an organization just as much as it does to the branching outward of an enterprise. The business is an Internet of Things microcosm with its own potential for digital enhancement. Direct feedback of the way a product is used, for example, can yield detailed information which can be used to drive product improvements. The Fish Wallpaper Company gets help from users who allow their anonymized app usage data to be transmitted to the company database. The app feedback data can identify preferred features, expose user interface problems, record hardware performance and predict component failure, allow a user to send comments and delineate user trends. So what could possibly go wrong? Some of the implementations mentioned earlier illustrate questions which may arise. Take the example of transmitting health data over the internet, or allowing one's mood to be assessed by artificial intelligence. What if the anonymity were to be compromised, the personal details appropriated? There are clearly privacy and security implications. And then there's the example of a service which makes its connection in the cloud. What if the cloud connection is broken? This could affect the system functionality in the apartment. In this case, a relatively minor feature of the fish wallpaper would stop working. But not all systems can tolerate interrupted service. Critical systems require an on-site failover in the event of internet disconnection. The intertwined areas of security and privacy can make or break an IoT IoS system. Security may be overlooked or underfunded until something goes wrong, when remedial action may already be too late. If privacy is not respected, customers may become disenchanted. It is the global nature of the Internet of Things and Internet of Services which makes a secure operating environment more important than ever. The Internet of Things has the potential to be of positive practical benefit on a hitherto unknown scale, providing it is developed with care and respect.